Thank you everyone for joining today for the 7th and final installment of CATIA University. Today we're going to be talking about fasteners and automated manufacturing processes. I'm Susan Crowden here at Vias 3D. I'm accompanied by Glenn Larson, Gerardo Ochoa, and Adrian Terral, all from Vias 3D. Next slide. So first, for the good stuff, for any of you who've been here before, yes, you know, we do give graduation gifts. We're expecting everybody to graduate with flying colors, but you must stay to the end of the class to be present to win. So you will win a $50 Visa gift card if you stay till the end. One person will get drawn. Not everybody gets a $50 gift card. And then for anyone who participates in all 7 classes, you'll be entered to win either a Space Mouse or an iPad. So I am in hopes that we do have people who have completed all 7 classes and are graduating. So we will announce that winner or both of those winners towards the end of the presentation. Next slide. Who are we at Vias 3D? So we're a Dassault Systems Platinum Partner, and we've been a Platinum Partner the last 4 of 6 years. We've only been in business for 6 years, so it took us a couple years to get ramped up. We're a Dassault Systems Education Partner. We have industry experience in multiple industries, including oil and gas, manufacturing, automotive, aerospace, nuclear, etc. Our team has grown to more than 200 employees, many of which have PhDs or higher accreditations in design, manufacturing, structural mechanics, fluid mechanics, electromagnetics, etc. We provide engineering and PLM consultancy, training and software support, automation and customization, and we have a presence around the globe with offices in the United States, Canada, Mexico, India, and a recent new addition, Turkey. Next slide. Who is Dassault Systems? So for those of you on this call who don't know who Dassault Systems is, they're the world's leading developer of CAD, CAM, and CAE software. They have more than 120 interrelated software products serving 11 industries. They have 22,000 people around the globe, 12,600 worldwide partners, of which we are one, with 290 plus enterprise customers. And they're about 5.4 billion in sales. So they're not a small company. What value do we bring here at Vias 3D? We bring connected collaboration, process discipline, and digital product experience using the 3D Experience platform. The platform technology includes social and collaborative apps, 3D modeling apps, simulation apps, information intelligence apps, all on one platform for a single source of truth. Next slide, please. So now I'm going to turn it over to Glenn and the technical team for the 3 key takeaways for this class today. Glenn? Glenn, we don't hear you.
Okay, thank you, Susan. And I wanted to thank everybody for attending these classes, whether you've attended just today or whether you've attended all of them. It's been a lot of fun putting this material on, and I want to thank everybody for your input on what material you'd like to see. So please, at the end, when we ask if we have a survey on what we want to see, please, please tell us what you want to see. So the 3 key takeaways today will be workflow optimizing for fastener creation, flexible fastener installation, and the reuse fastener data for simulation. The great thing about fasteners is that is an application to itself that lets you instantiate fasteners using many different techniques, and those fasteners can then be reused for simulation to validate that you placed them in the right place and you're going to cause any problems. Next slide, please. So today I'm going to introduce both Roberto and Adrian. Gerardo is our senior simulation engineer, and Adrian is our CATIA applications engineer, both of whom have a lot of expertise in the 3D experience. And with that, I'm going to hand it off to Adrian. Adrian?
Thank you, Glenn. So, well, let's start with the fasteners part. I would like to start. Many of you may not be familiarized or have been working on 3D modeling apps with fasteners. So a fastener is a part that is created on the 3D experience, and this is created by the designer, and it's meant to hold or fasten 2 or more pieces together. On the right, you can see different examples of fasteners, but they are not the only ones. As you can see, we have a set of bolts, screws, nuts, but we can have also rivets, and going further than that, we can have, for example, welds, adhesives, and different kind of elements that join these 2 elements together. So let's take a look of what we can achieve on the 3D experience by using fasteners. So first of all, we will use an application which is dedicated to design the fasteners across all industries. It supports the modelization of different types of fasteners. As you can see, we can have single fasteners, a bundle of fasteners, and we can have bit fasteners. The technological view of fasteners can be defined to specify if the fastener is based on welds, bolts, modeling, etc. So you can see that we got different applications for different industries. The role for the transportation and mobility role, it's the body fastener designer, but we can have that on the aerospace and defense industry. You can have an example here, and further than that, we can have that different ways to instantiate these fasteners to then use simulation apps. Gerardo will talk about that, and manufacturing apps. We have some examples in here. Okay. Now, fastener design enable us to work with 3 types of fastening families. A single fastener that we can spot. This represents a single spot fastener. You can associate various fastening processes such as weld, adhesive, sealant, rivet, bolts, and clinch with these fasteners. Okay, then we can have a set of fasteners, which is assembly. That means that this represents either an assembly of a bolt and a nut or a rivet, and you can control the shape of this fastener and all the fasteners together. Very important thing is the kind of geometry that we will use to create this assembly of fasteners, and that would be the skeleton, which is a wireframe geometry that could be a set of points in which we want to define our fasteners, or it could be a curve along with we want to create the fastener. And finally, we will have the bit fastener. This represents very associative geometries, various fastening processes such as weld, adhesive, and sealant with this fastener. So this is what we can represent. For this, we will use a curve or a geometry, which we will put this fastener along it. Okay, so I will continue to a video. Let me explain to you what we can achieve using the CATIA application, CATIA Fastener, inside the body fastener designer role, which is the one for the transportation and mobility. So we can optimize a flexible workflow to easily define a set of fasteners. What you can see is that we got the skeleton defined, we got the 3D parts that we may have from sheet metal design, or if you're working in a different industry, it may be composites, right? So what we do is select this set of points, and we will get something called the key vector. The key vector, it's a vector that defines the position of the fastener. So we can go from a unitary fastener defining a catalog to create this bundle of fasteners and position them automatically on our assembly. You can see how the parts involved will be used to define this set of fasteners. We can then stack different kinds of fasteners from a catalog, and that's very important because that allows us to reuse the data. And finally, once that we select that fastener from the catalog, what we will do is create all the entities into a single bundle on our operations tree. So that will be able to be handled very easily and very quickly. You can see this process. What we are doing right now, it's position these fasteners on the right view. We select the parts involved. We got two for this case, the one in blue and the one in green. Okay, let me show you a different example now for a different industry. This one is the fastener designer role inside CATIA, but applied to the industrial equipment industry. Okay, so let's play this. Okay, so you may remember this example that we got one of our previous class. What we are doing here is position rivets on our sheet metal design, and this is a spot fastener. Okay, then what we do is select that spot fastener. All the characteristics may be on the catalog that we previously defined. So in this case, we will position these rivets. And very important thing is that we can position that by applying a set of rules. For example, if you want to apply a set, in this case, this is a bolt. And if you want to apply these fasteners along a curve, and then you can define the minimum distance between them or the maximum distance between them. And once that you have instantiated all the objects on the design view, you can quickly generate reports. So that's a powerful tool that will give us all the information about the fasteners that we are creating in the 3D model. Okay, so I think that's it for the designer role. Let me talk about a little bit about the workflow example, how we can achieve and how this can be integrated into your design process. So we got several options. We can part from a legacy software such as CATIA V5. We will have the root CAD product, and that means we will have the 3D CAD parts, which is all the structure, all the parts created, and then we will have our skeleton. That's important. That's the wireframe geometry that we will use to position all the fasteners. Okay, so we will usually come from composite design or sheet metal products. Then we can import that native data. It could be V5, for example. This CAD product, CAD part, we can import that into the fasteners database in the 3D experience. Okay. Then using the fastener apps, we can create a template of flexible fasteners. That means we can create several bundles of fasteners to create and to select among all the ones that we are using into one program, for example, and they will be adapted for stacking. Then using the fastener apps, we will define the fastener objects. The position will be driven by the skeleton. That's the wireframe geometry that, for example, we're able to see here. We got a curve, and then we may define the kind of instance that we want to use. That would be the stacking part, instance of 3 parts to fasten. And then we can define a set of rules, for example, the minimum distance. We can set the key vector and position the fasteners on the side that we want to use. Then we can, if you're working with a legacy software, you can update that CAD part, or you can import a new version into the 3D experience database. To finally use interference app that enters a little bit into the simulation parts. So we can use the direct usage of fasteners and 3D parts, for example, for clash. This would be a clash analysis. And then we can reuse that single data, and that's very important. because this data that the software pull out when we create our instances can be used in different applications. So at this point, I will hand off to my partner Gerardo, to my colleague Gerardo, which is going to explain how we can use this data, how we can reuse that into simulation apps and manufacturing apps.
And this is Glenn chiming in here. Right before we switch over to Roberto, one thing I wanted to mention is that, you know, these are what are shown are a lot of best practices. I also wanted to point out that if you're using the Fastener app and you don't have any skeleton or hole data, it will instantiate fasteners across an edge. So there are other ways of doing it. Skeletons do not need to be created, but they are best practices. You know, because then you can control that from a control point. So I just kind of wanted to throw that in there, Adrian, that it's not mandatory that you build a skeleton, but it is a best practice.
Okay, great.
And with that, we'll hand it over to Roberto. Roberto?
Thank you, Adrian. Thank you, Glenn. Next slide, please, Adrian. Before we start the video, I just would like to make some comments before we go through the workflow. So what Adrian just explained to us, I mean, this is more related to, you know, managing the product structure and the design aspect. And at some point, we might need to perform simulations, right? And the way we are doing the fasteners installments will have a lot of impact on the structure behavior. So when we have, you know, when we perform simulations with large assemblies, sometimes in the simulation domain, instantiating fasteners could be a tedious task. So this fastener application from CATIA makes I would say, the simulation analyst life easier, because the simulation model can gather the fastener information from the product structure and create the necessary connections automatically without with very minimal user intervention. Okay, so what we will see in this workflow is how simulation analysts and also non-simulation experts can perform simulations reusing the fastener data. So Adrian, can we start the video? Okay, so this is a workflow showing the collaboration between CATIA and Simulia applications. So the first step in this workflow will be the flexible fasteners installment on the product structure. So at this point, the user is just defining the type of fasteners that will be instantiated in the assembly. So by doing this task, the simulation model will be able to read what we're just doing here and make the necessary connections for the simulation. In that way, our simulation model will represent better the real conditions of our, in this case, the assembly for the transportation and mobility industry. So after doing this, the first step will be creating the simulation model that will represent the assembly. The first step will be creating some meshing rules. Meshing rules is just about defining the meshing criteria to have a high quality finite element model. Okay, meshing rules is just a set of, I would say, conditions that will measure the element quality. And these rules, one of the main goals of using these meshing rules is because we are going to generate the entire finite element model of this assembly automatically with minimal user intervention. So in order to do this, we have to tell the Simulia application under which conditions the application will build the mesh of the entire assembly. Right now, we're just defining to which components the meshing rules will apply. We're just defining the meshing rule definition and also how the execution will be performed, because this will mesh automatically the entire assembly, and we can also use hardware resources, not just using our computer, but also using a remote hardware. That's also possible, and we can also define the number of threads available in the hardware to automatically create the mesh. So, and after doing this, we just have to update the product structure, and the simulation model will be created automatically. As you can see, the meshes are being created automatically. So right now, we just have the FEA model defined under the product structure. We're just visualizing the shell mesh that has been created. Next step will be reusing the previously defined fastener data. So the finite element model will be able to read it and create the necessary connections automatically. So right now we're under the Simolia app, and we're just selecting the import fasteners command and reading the fastener data from the product structure. And as you can see right now, all the points, yellow points that we're looking at are coming from the fastener data created from the fastener application. In this way, we're defining the connections in the finite element model, and we will run a very, let's say, an example running a frequency simulation considering these connections. During this workflow, we will explore different configurations of this simulation, and we will be basically changing the fastener data to see the effect of this data in the simulation results. So after performing the simulation, this is the frequency simulation, we will be able to see the form modes at different frequency levels. And by seeing these results, we can see that at some frequency levels, the structure is having some deformations, unexpected deformations, and this is due to the lack of fasteners. So very easily, we can go back to the product structure, edit our fastener data, and update the simulation model and rerun the simulation again. I mean, this is with no manual user intervention to define the fastener position at the simulation level. So in this case, the first thing we're going to do is diagnose the fastener data. I think Adrian mentioned before, we can define the minimum distance between fasteners, and if we are not fulfilling these conditions, the fastener data will not be read in the simulation model. So in this example, we are not in compliance with this. These fasteners are very close. So the user will just perform a modification in the distance between these two fasteners. We just have to go to the wired data that Adrian just explained to us. We will measure the distance between this wired data, and we can, just by modifying the distance, the fastener data from the product structure will be automatically updated, and so the simulation model will be. This allows to, by working in this environment on 3D experience, this allows us to work with real-time data using PLM objects. So after updating the fastener data, we just have to go back to the simulation model and update the simulation model using the new fastener data. with the update. We're just checking the new fastener data, and I mean the green color next to every fastener means that they are okay with the fastener installment conditions. So right now we're just saving the model, and we will go back to the simulation model, update the simulation model, and the new connector will be automatically placed in the assembly. Okay. We just have to perform the update, and we will see in the left side of the assembly, we just have the two connectors very close to each other. We just have to update the new fastener data, as you can see here. We import the fasteners again, perform the update in the simulation model, and you'll see that now these two connectors are positioned as expected. And then we can just rerun the same simulation again. As you can see, until now, there is no manual definition of connectors. Of course, that can be done, but you know, if when we're working with these large assemblies, it could be a very time-consuming task. So by using the product structure data, we can really, you know, save a lot of time. Right now, we're just running the simulation again. And after running the simulation, we will again check the frequency levels at different deformed shapes. We'll still have some undesired deformation on this model. We will go back to the product structure data and perform the necessary changes to the fasteners. Before we go to that step, we will just make a comparison between the previous simulation and the new simulation. And I mean, in this way, we will be able to see how is having impact the new fastener data in the simulation results. As we can see in the different models, there is a minimal impact of the new fastener position on the frequency levels. We have basically the same frequency at the same mode numbers. So this means we still have to do corrections to the connections. And, you know, instead of manually edit the connections on the simulation model, that of course that can be done. But in order to keep, you know, the product structure data updated, we will go back to the fasteners design and perform the necessary changes. Right now, we will be using a new set of fasteners, and we'll apply this to the product structure. We will include a different set of fasteners in different regions. Right now, we're just opening the new fastener data. We just have to open this at the simulation model level, perform the necessary updates, and the model will be ready for the next simulation. So we will include a new couple fasteners in these regions. As you can see here, we're just placing the wireframe data and including the new fastener here. The same will be done on the right side of the model. New fastener will be placed here just by selecting, defining the new wireframe data here. We're okay with this new fastener. And next step will be, we will just need to update the product structure and go back to the simulation. And the simulation model will be able to update and read the new fastener data, and the connections will be there, ready for the new simulation. Adrian, can you help me just moving forward the video? Like, no, just a couple minutes. Yeah, that's okay. Okay, so now as you can see, there is the new Fastener data in the simulation model where we just read the new fasteners. And by just updating the structure, I think I've said this many times now, we can run the simulation again. And after doing these steps, we compare the new simulation results. And I mean, in this way, we will be able to measure the impact of these new fasteners into the form shape. We just define new frequency response analysis, 20 modes, defining the number of cores to be used. Now we have the results. Okay, we're just looking at the new frequency levels at different deformed shapes. I mean, as you can see until now, it is very easy to use updated fastener data on this. I mean, the same will happen if we perform changes to the CAD. I mean, the focus today is the fastener data. And now we will use a different example, not just by using point fasteners, we will use bead fasteners. So in this case, we are representing some kind of seam welds. We can just define the type of material to be used in this seam weld, the size, which kind of elements for the simulation model we want to use, and the simulation model. I mean, this is at the fastener data level. After defining these new fasteners, the simulation model will update automatically. We'll see here, we're just defining the new material, the size of the bead fastener, the spacing that will be used here. And after doing this, we just go back to the simulation model, update the simulation model, and now the bead fastener is well represented here. We will just include just, I mean, this is an example of adding manual connectors on the simulation model. This is not part of the fastener data structure. This is at the simulation level. This is just rigid connections to improve the frequency levels for the simulation. The fasteners imported from the product structure have a flexible behavior, and this is the main difference with these connectors. These connectors is just rigid behavior. So we're adding some stiffness to the assembly. Okay, this is ready. We just have to rerun the simulation again. The connectors are updated, and we can continue with the simulation execution. And after executing the simulation, we will be able to compare the simulation results with the previous configurations and the improved configuration. And we will see that the frequency levels are much higher compared to the previous configuration. Adrian, if you can help me moving the video towards the end, like, yes. So this is the result.
I wanted to mention here, I was going to throw in one of the things, like all CATIA, Simuli, and Delmia applications most of the parameters you put in can be added as parameters. So future down the road, when you build these processes and you're doing optimization, or you want to do some studies, you know, all of the functions, even in the Fastener app, you can use parameters for. So I thought I'd just throw that in there, Roberto.
Yeah, that's correct. Okay, the final step is just compare the simulation results with the improved connections and the previous configurations. And we'll see here that the frequency levels are higher at the same mode numbers as expected. I mean, that was our target. The simulation, the frequency levels are higher compared to the previous configuration, and we are getting the expected deformed shapes. Everything is now connected. And with this, I will finish my intervention. Thank you.
Thank you, Gerardo. Okay, so finally, let's talk about all the benefits of implementing these roles into your processes. So first one is that we can create an efficient, scalable, faster design that can be bundled, which allows data to be used on a wide range of complex programs. That means that we can design these elements for one time, then reuse the data, create a set of catalogs into our database, and then if we're working on a different program, just call out that elements directly from a catalog, reuse the data, and also do that process as simple as we have seen that it is into different programs. Okay. Then, as we have seen, this allows for a unique concept to detail design. We've seen that on the first part of the webinar, in which you get your 3D CAD parts and your assemblies, and you define a set of wireframe, or you use existing geometry like an edge for bit fasteners, and you can get to a very detailed design inside the platform. And then you can reuse that data to use simulation and manufacturing processes. As you can see, all the processes are very close to each other. You can reuse data, and you can go directly from design to simulation, and you can perform modifications very quickly. So this is a unique way to do it. Of course, we are supporting concurrent engineering, lifecycle, and change management, and downstream processes. So we can use, and we can once again take advantage of these functionalities to manufacturing simulations, to create reporting, and it's a very fluid and very good workflow in which we can do this. Finally, you can enforce your company's standards and rules usage by defining these parameters that Glenn mentioned, by creating your own catalogs of fastener elements, and you can quickly call these, apply these standards, and apply these rules into your design processes. So, well, that would be it for this. I will return to Susan or Glenn.
Thank you, Adrian. And thank you everyone for attending today. So please let me know if you have any questions. Go ahead and put them in the chat box so that we can read the questions. I do have a couple already, but please feel free to go ahead and put them in. And then another thing that I would like for you to do is let us know if you want us to continue this series. Let us know if that's the case, that you do want to continue this type of a series. What types of topics would you be interested in knowing more about? This is all about doing this for you guys and understanding what's going on with CATIA and all the new features and functions that they have. So please let me know. Okay, so I'll start with the first question, and please go ahead and don't hesitate to put some questions in the chat window, or the question window, I'm sorry. That'd probably be the better place. So here's a question. Do the fasteners get positioned automatically?
Yeah, well, as you can see, we need to define first a set of geometries. The fasteners get positioned automatically because it uses something called the key vector. So the key vector will use all these input data, which are the parts, and which are the geometry, if you want to define that, or maybe existing geometry like an edge. Then the fasteners will be positioned in that single point or that set of points or that edges. And then by using these key vectors, we can position automatically the data. So that means they will be using the normal planes to that. And as you can see, that's a very quick way to define like a huge bundle of fasteners. So yeah, there are tools that help us to position the fasteners, and it gets automatically positioned on the skeleton data or wireframe geometry.
Okay, this might be a similar question. It says, which geometry do I need to create to position fasteners?
Yeah, that's a good question. Also, as Glenn mentioned, we can have, and that a best practice to define the set of points, to define your skeleton, but you can use a single spot to define a fasteners. We saw that on Gerardo's video, in which when he needed to create a modification for position at different fasteners that were too close, and you just need to define that wireframe data that could be as simple as a single point, and you can use that.
Okay, thank you, Adrian. Here's another question. What is the advantage of using the fastener creation role?
Well, we got several of them. Just let me guide you through some of them. So first of all, it's that you can reuse that data very quickly. We have seen that. It's an optimized, flexible workflow that can efficiently use or that help us to create fastener designs. For example, we have automate stacking computation, as we have seen. Something that we didn't see on this video, but it's a huge advantage of using this role, is that we have a very complete fastener analysis and review. So we can quickly generate reports for using this role, and we can put that, for example, into our BOM, into the data that we wanted to create. Those bundles are created automatically, and we can generate reporting from them.
Okay, thank you, Adrian. Here's the next question. It might be for Gerardo. It says, I can see from this example that the weld fasteners are connected to the simulation model. Is this the same for bolt fasteners?
The short answer for that is yes. I think we were very focused on weld-like fasteners in the video, but with the same application, users can define bolt fasteners. And a very, I would say, good advantage of this is that regarding simulation, the simulation application will know that these kind of connectors are bolted connectors, and by doing this, we'll also provide the ability to apply pretension to the bolts for simulation purposes. So yes, it is basically the same workflow, but I mean, by using bolt fasteners, we will have different options regarding simulation.
Okay, thank you, Gerardo. Here's another question. Do I always have to create meshing rules from scratch?
Not really. I mean, in this example, we just define manually a new set of meshing rules because, just wanted to highlight that we can define these rules and be considered for automatically building the simulation model. But there is a default set of meshing rules available, and this default is meant to use a set of rules that will fulfill the element quality needed by Abacus, which is the structural solver in the simulation, in the Simuli applications. But I mean, the short answer is no. There is a default set of meshing rules available.
Awesome, thank you. That's all the questions that I have at the moment. If anybody else has any more questions, please don't hesitate to go ahead and put them in the chat or the question window.
And I want to add to one of the answers that Adrian had with the advantages of using this application. So, for example, many of us are familiar with, CATIA V5 or other methods of instantiating fasteners, and your options were always very limited. And so some of the things that the video may not have shown or may have shown are that if you instantiate a bundle of fasteners across an area and they're not all going in the same direction, you can actually change the direction. So in other words, if you have some bolts going in from one side to another and that switches direction, you can change that in one bundle here. So you don't have to create all of these instances. And then, like before, to have the fasteners constrained into a model, you would have to have them individually listed out, as to where in a bundle here, they're kept within themselves. And so it kind of makes your containers smaller. And so that's one of the other advantages, outside of the fact that you can use the simulation data. And we can also, if you have fastener representations, when you instantiate these bundle of fasteners, those representations can be instantiated as well, so you can see what they really look like. So I thought I'd throw those couple of tidbits in there, Susan.
Okay, thank you, Glenn. So with that, we are concluding our session, our CATIA University, and we'll be back with some other set of information for the general public in another format. So thank you once again for joining today, and good afternoon, good evening, good morning, no matter where you are. Thank you so much.